Okay, I unmuted the mic, so whatever you say will be recorded. Okay, great. So it's really nice to have Zhiyuan speaking. I talked to Zhiyuan a lot, but still looking very much forward to hear him today. So as you know, Zhiyuan is a faculty here, I think, for 3 years now, and also a father for 6 months now. Okay, so this is his first research TTIC talk as a father, and will tell us. But I think he'll tell us about other things today. And John has been working. Okay, I mean, Zhiyuan, I think will only tell us about a few of the things he's working on. But if you have not yet had the chance to talk to him or I encourage you to do so. So
thanks, Nati. Okay, so today I would like to talk about one line of my work in my group for the past few years. So it's about another geometry in modern learning. I think it's an exciting time to talk about this because there's really not too much empirical progress in the past 10 years until 1 or 2 years ago. So basically we are using Adam, like variant Adam W. It's like a paper with more than 200,000 citations now, and it's this very simple heuristic deductive rule. Like you have maybe a proof, but it's maybe partially correct, but doesn't matter. Don't hurt its empirical success. So basically, if you have never seen it before, so just let me explain it to you. You have momentum, which is empirical moving average of the stochastic gradient, and then you have like second order term. The point is that you have to do this in element-wise product, and then you do this preconditioning element-wise. So the point is that you're doing it element-wise, and it just works. And in most of the cases, you can just use the default learning rate and plug into your your deep learning laws, like some toy experiment, and it will work without worrying too much about tuning. However, there's a new challenger for this default optimizer, whose name is Mu, emerging, I think, towards the maybe second half of 2025 to 2024. It's an abbreviation of momentum orthogonalized by Newton-Schwarz. So you don't really need to know the Newton-Schwarz. It's not the point of this paper, but if you're curious, just this is an iterative algorithm to implement this operation in this Mu algorithm. So in some sense, the main reason that this algorithm becomes popular is not because it's a new algorithm, but this is really people find a way to implement this efficiently and actively to try to implement this in large-scale deep learning practice and succeed. Okay, but this numerical efficiency is not the focus today, so we're just going to use this mathematically correct version, which is just this matrix sum operation. So give you a matrix, you're going to do SVD for this matrix, and then you're going to drop these singular values and just keep UV transpose. So it's always going to be a orthogonal matrix, the return. So what Mu does is take the EMF, the stochastic gradient, and then you do this single update, and then you subtract from the current parameter. And there's a Chinese startup company called Kimi. They did a large-scale test for this new optimizer. This is a comparison between Adam W. So you can see it consistently be faster than Adam W. And they also really switched to this. They are like the current generation of model training, like Kimi, I think 2.6, from Adam W to Mu, with some like customization to different layers. And also, this success of Mu is not only limited to Kimi, and the most recent model of DeepSeek V4 released in this month also use Mu. And yeah, I think DeepSeek V4 is already a pretty large scale model. I think around maybe one T parameters. Okay. So I would regard this kind of like the power is like validated in a pretty large scale. So the Mu update is somehow can be derived from a very simple principle, a unifying principle, which is steepest descent from the sum norm. And in this case, it's spectral norm. So more generally, you can choose an arbitrary norm you like in the parameter space and choose the unit norms descent direction, which gives a gradient takes the minimizer of this linear function within this unit norm constraint. And the examples, you can take L2 norm and you go normalize the GD, and you get infinity norm, you get sun GD, and you can take of course just the operating norm, which is a spectral norm, and you get momentum free mu. So momentum is a separate story. And you can also put the variance of like layer-wise mu into this framework. Basically, you're going to apply this mu to every matrix parameter in the network. And even this you can return as a steep descent with respect to a general norm for the entire parameter space, which is the norm you're going to use is the max of the spectral norm of each layer. Okay, this is still like steep descent to a single norm. Okay, now it comes to geometry. So more generally, you can think this is determined by the geometry algorithm. So geometry basically is some like a map tensor gradients into an update. And I think in a general notion, you can think geometry is like local proxy for x. And you are taking x plus, which is next step, by minimizing this function. And in this talk, we are going to just most interesting the case where this geometry is really just a function of the norm between x and y. So it's like independent of the position x. It's only depends on displacement. And this already gives it like two large class of algorithms which we usually talk about. The first thing is unnormalized descent, including like normal GD, and the other class is like normalized steep descent. So in this talk's geometry basically will be equivalent to some norm. Okay, so the success of mu has already like reactivated the research in kind of this area. So people, question.
So can you go back to the previous slide? So this is essentially projected gradient descent.
Yes, you can think so. Projected. And it's not like projection, but you're doing like a minimization over domain.
But you're
and here I'm not. I didn't put the domain constraint in this argument, but if you do, you will get that. But I'm not.
Oh, I see. Okay.
So if you do this, you can see your like indicator function for 0, 1, right? So you're already constrained that your norm can at most be 1. So it's like normalized steep descent. So you can make it projected, but I'm not doing that here. In practical great. Okay, so yeah, so the success of mu basically like kind of like reactivated this research area of like optimizer, and people like started again to try to improve or come up with better optimizer by designing, coming up with new norms, new like compositions, or maybe even norms with different norms with combined with different adaptive methods like Adam. Maybe you can first do like Adam, and then you can do mu like this matrix sign of the update of Adam, like things like that. But this does not answer the question of like why you want to choose this geometry like over the other geometries. So to answer this question, we really need to kind of like dig into the property of the loss function and data and this property of architectures. So in particular, in this talk, I would like to discuss these 3 questions. The first question is about adaptive optimizers. So it's relatively easy to see that given a steep descent with a fixed norm, like what you can expect, but how should we understand Adam, right? So is Adam should be understood with like fixed norm or something else? Can it be put into this framework? Has its success, like does its success of Adam has anything to do with a recent trend of like this normalized steep descent? And second question is, given a bunch of like geometry-related assumptions that we can prove these kind of like algorithms work, like how do we actually compare them, and can we actually like exploit them and by designing better algorithms? And third question is actually how does these geometry-related assumptions, which allow us to prove like nice results for these algorithms which are different from SGD, come from? Can we actually show the origin is rooted in some kind of like architecture or data, or like anything else? Are they universal or just tied to this transformer architecture? So understanding this will help us to design like next generation of optimizers and even better optimizers. Okay, so this is the roadmap of talk. So I will start with joint work with my student Shuo Xie and Ming. Is Shuo here? Yes, Shuo is here. I'm Ming here. Okay. So the first work I'm going to present is trying to convince you that to understand the performance or like the advantage of Adam over SGD, you really need to go beyond L2 geometry. So this question has been asked for maybe around I think 7 or 8 years in this like better community, like why Adam outperform SGD. So there are like a lot of explanations. Like some of them look like this. For example, there's explanations say that adaptive scaling under generalized smoothness, which is a notion called L0, L1 smoothness, where you don't want to assume the hashing of the loss is bounded uniformly, and they only assume it's bounded uniformly, bounded by some constant plus some other constant times the gradients of that point. So they allow hashing to be unbounded, and still we can prove convergence with Adam. So this is like relaxation. And other assumption includes like robustness to heavy-tailed gradient noise. Like you can assume your gradient noise does not have very good concentration, and you want to prove like high probability bound. Like in that case, Adam will be useful. And also to unstable gradient magnitudes, similar to heavy-tailed gradient noise. But the caveat of this argument is that they kind of like only explain why some kind of like adaptive scaling is useful, but they don't really explain why you want to do particularly this coordinate-wise adaptivity versus this just a much simpler or cheaper version of global adaptivity, which I call LSGD. The name is not by me, it's by some other people in the literature. So the difference is that in LSGD, you don't do coordinate-wise preconditioning, but you only maintain like 2 bits of maybe 2 parameters extra to keep the global L2 norm, averaged by the number of coordinates. Okay, so basically this algorithm has all the benefits claimed here. And we'll prove these benefits. Basically, you don't really care about the norm. You care about dependency on T or whether you can converge or not. And you know, in finite dimension, all the norm effects are the same. You don't really care about how do you assume your smoothness. So if these are all explanations, so why don't we just use this? And this will save you like so much memory for parameters, and you can train much model with the same GPU. So the answer is basically no. So it's basically this has some benefit, but it's going to be slower than Adam, so it doesn't work to switch even for the memory efficiency. So on the other side, traditional like optimization convergence bounds based on L2 geometry can also not distinguish Adam from LSGD. So basically, in all the regimes, if you look at dependency, the rates on number of steps, they are the same. Okay. In terms of T, and SGD is already minimized optimal under like standard Euclidean smoothness assumption, and other maybe non-smooth assumptions like the stochastic setting. So the necessary logical implication here is that if Adam really outperforms SGD in practice, the explanation cannot come from the worst case geometry, worst case L2 geometry alone. And the natural hypothesis here is that realistic laws have finer and non-Euclidean structure that Euclidean quantities erase. Okay. So the lower bounds there are valid, but the point is that they are just too crude. You don't capture the next property that we really care about in practice. So therefore you have this gap. So the point of this paper is really just to try to test this hypothesis. So we want to design some experiment or like some test to destroy this coordinate structure while preserving the Euclidean quantities and recheck the performance of Adam. So we give a rotational diagnostic to the loss function. So basically, you can do is like what you can do is pick an arbitrary orthogonal matrix and you can rotate the loss. And this preserves all the Euclidean quantities such as like L2 smoothness and L2 radius of the minimizer and the global gradient scale. You can even prove a stronger property that the L2 invariant optimizers like GD or ADAS-GD will have invariant trajectories. Right. But the point is that Adam does not. Adam has coordinate-wise adaptivity, so if you rotate the rotation, then the trajectory changes fundamentally. And the point is to see if Adam behaves much worse in this case, because you're really introducing some worst case regime, which is not natural in practice, but the theory actually use that to prove lower bound for Adam. So this is the experiment we do, and we have 4 setups, which are Adam, ADAS-GD, and SGD, and the new one is this rotated Adam is a green line. So it's basically just Adam applied on this rotated loss, or you are applying Adam on ordinal loss on a randomly chosen coordinate system. So it's not completely randomly chosen because to keep a random matrix of size like 1 million by million is huge, it's very expensive. So we're not even doing random, we're just doing some kind of like rotation, maybe it's like composition of smaller random blocks. But even with that, we're already making Adam much worse after random rotation.
I'm curious, it's still better than, I find it surprising better than SGD. Is that because the rotations are partial? I mean, if you did a true rotation, would it be?
I think that is a gap where this global adaptivity really works. So you see, this is a ADAS-GD. It's the adaptive version of SGD, and it's SGD. Okay.
Oh, I see.
So this really works. So I mean, it's reminds me of my job talk. 3 years ago, I gave a job talk here. Maybe 4 years ago, I gave a job talk here. At that time, I talked about some attempts to make transformer scale invariant and try to train it with SGD. Okay. So in that case, you can think this training transformer, scale invariant transformer with SGD is basically running ADAS-GD on the unit sphere. So it's the same. At that time, I already realized it works, but it's not going to be as fast as Adam. It still helps you.
It's not the same as rotated Adam, though. It's not the same as
it's not the same.
It's randomly rotated.
Yeah, but
Adam.
It's better even.
Yeah. I'm surprised that. I guess I'm surprised that randomly rotated Adam works better than
SGD.
Oh, maybe it's because of the momentum. The SGD presumably also has momentum.
It has momentum, but SGD is very unstable. You can see this spike. You basically cannot use larger linear event. You're using very small linear.
Oh,
yeah, it's like an issue. Very unstable. Yeah, so this is the observation. And the takeaway is that you need rotation. So the takeaway that a rotation invariant theory cannot really explain rotation sensitive advantage. So if you want to explain the advantage of Adam over SGDU for the most of training we see in practice, you do need some like theoretical concept which is not rotational invariant. So that's the punchline of this experiment. Because otherwise, if you can explain in rotation invariant regime, you're basically going to explain why this green line is better than this orange line, which is not true. Okay, so you cannot explain that. You can never explain that. Okay. So in the second work, we are going to talk about our initial attempt to trying to look for this characterization of some geometry property that Adam can actually exploit to go beyond like this L2 thing. Oh, it's actually true again. So today, for all these 5 papers show very few codes. So one main contributors. Okay, so so the answer we had for this initial attempt is L infinity optimization, L infinity constraint optimization, or L infinity normal geometry. So for this, I have to talk about the background, which is Frank Wolf, something I just taught in my optimization course. So Frankhoff is a very classical optimization algorithm invented in 1956. So basically, it says that you have a convex set, closed compact convex set, and you have smooth function over that, smooth convex function over that. And the way you want to optimize is that you want to just have a linear minimization oracle. So you give a linear function over this convex set, and you can you assume you can find the minimized linear function over this convex set easily. And with this assumption, you're going to define an algorithm look like this. So each time you query the linear minimization oracle to get the minimizer of the current gradient in this convex set, and then take a linear combination of the current point and the minimizer, and you iterate. That's it. It will for t steps, and you can get this rate. L r square over t. So basically, L here is the smoothness of this convex function with respect to this norm, and r square is basically the radius of this convex set, and the norm can be arbitrary. Choose the arbitrary. Okay, so what's the relationship between Frankhoff and today's deep learning? Well, this almost the same thing, because if you think about normalized steep descent and with weight decay, which is something we all do today, they're basically the same algorithm. So the claim here, the formal claim here is that if you do normalized steep descent with weight decay, which has the updated rule like this e to the t lambda is the so-called weight decay, and dt is basically the steepest descent direction with respect to this norm. Okay. So it's basically Frankhoff on a norm ball of radius 1 over lambda, and you have your learning rate set to, you have your Frankhoff learning rate set to be the usual learning rate times lambda. Okay. So basically, like mu is Frankhoff if you don't have momentum, this is the claim. So it's like very old algorithm. So really the new thing that will become popular is that we found the efficient implementation for this linear minimization oracle over fractional ball. Okay. So yeah, I would like to thank Nati for hinting me on this by sharing with his like optimization notes. While I was doing research with Shaw, I was also preparing for the optimization course in 2024, and then I realized it's the same thing. Like,
So for this equivalence, it kind of relies on having a pretty aggressive weight decay. Is that basically correct? Because the Frank-Wolf can only go inside of a bounded size ball, right?
Right. So that this, you can never go outside this ball, and this is something. Yeah. So it's very easy to prove this.
But yeah, this is like if you don't have the weight decay, there's no such equivalence, right?
Right, but actually you need weight decay.
Oh. Or in practice.
In practice, you need weight decay. So when we talk about the algorithm, you always have weight decay. And it's important hyperparameter too. Yeah, so okay, so what has this to do with Adam? Right,
Sorry, so in addition to the norm, there's also some delta norm coming in here, right? Because the weight decay, I mean,
no, there's no, that's point. So
where's the
weight decay is okay, weight decay is I think I have slides. I have a slide.
oh because the weight decay is relative. It's not really weight decay. I mean, it's
So weight decay is not L2 gradation. Weight decay is just a linear operation. Don't need a norm even.
Yeah.
It's in linear space. And L2 gradation is really something you need geometry. And I think this is a kind of good answer to the question, to debate on like, whether you need weight decay or L2 normal gradation.
so right. So this is invariant to. I mean, this method is invariant to linear transformations if you transform the norm also.
Yes. Especially just limiting to this convex set and this. So it's like a very elegant way to see, I think, Zhiyuan's new algorithm, basically Frankhoff with momentum. And we do have like in literature we do have convergence proof for Frankhoff with momentum in stochastic cases. It's not very coming from nowhere.
Right.
Good. So okay. The question is what has this to do with Adam? So it comes from this connection between Adam and SunGD. Okay, so it's obvious that if you view this, if you view SunGD in this way, you're seeing like SunGD is like Frank-Wolf over infinity norm ball, and of course you're thinking like just doing infinity norm constraint optimization, which is obvious. At least for convex functions, if it's non-convex, then they're doing something else. Yeah, but the big intuition that if you have Adam with beta 0 being 0, you just and you don't have momentum, you actually become SunGD. So there's a lot of people like arguing it's kind of like an intuitive way to understand geometry of like Adam, including like Jeremy Bernstein, who is the main author of the Mu. But if we want to more formal treatment, it's actually not obviously SunGD. A simple reason. A simple reason is that if you think about the point that Freddy just made, for SunGD you can never, with this update, you can never leave the ball of like 1 over lambda, right? Because the movement speed of SunGD is controlled by eta in every step. So this contraction always keeps it in this invariant state. This is obviously not true for Adam, right? Adam can locally have a much larger step size. If you happen have seen like a bunch of sequence of small gradients and you have one big gradient this step, you can have a very huge step. So it's not obvious to see the connection between Adam to SunGD when beta 1, beta 2 are in general position, meaning they're not 0. So the question here that is Adam still kind of like steep descent in the infinity norm. Like in what sense can we say Adam geometry is infinity norm? Okay, so this slide is basically for the definition of Adam W, like we need like waiting here. But these two variants are basically answering Nati's question on relative gradation versus weight decay. So we're talking about the green version, which is actually weight decay.
What's the green?
This version.
Oh,
Sorry for that.
Okay.
Apologize for Cloud's choice on color. No choice. Good. So we're talking about the green variant of the algorithm instead of the red one. So there's a paper called Adam W, which is just to compare this empirical performance of Adam for these two variants, and it seems green is consistently better and have better. It's easier to tune its parameters. Okay, so people think that most people just do this green version. Right. So it turns out we can actually prove that Adam W has something to do with infinity norm. It's kind of like, in a sense, like implicit bias. We cannot prove it's a direct optimization result, but what we can show is that if it converges with a non-trivial learning rate, meaning the sum of learning rate is infinity, so you're not converging just because your learning rate goes to 0 too fast. And with this non-trivial learning rate, and if Adam W converges, you actually can prove that this convergence point must be a KKT point of this constraint objective. So here there's some like non-trivial technical results like about how to deal with this fact that Adam can temporarily locally make steps much more than eta in infinity norm, but it turns out when you converge, eventually you only can converge to these KT points. And when the function is convex, it gives you a global minimizing. Right. So this is our first attempt to try to connect Adam with some like non-Euclidean norm. And this is not really kind of like the original intention for this research. It's more like byproduct towards finding a really actual correct geometry for Adam W. We want to still prove more like optimization bound end-to-end instead of just like asymptotic implicit bias. But it turns out, or like at least it seems it's hard to just use infinity norm smoothness to prove convergence result for Adam. So still we don't know how to do that yet, but later in another paper we identified another smoothness notion which seems to be more intrinsic to Adam. And this is, we call like adaptive smoothness. So this is a joint work with Shuo Tianhao, who was a RAP here, and he's now an assistant professor at UCSD. And to other collaborators from Google, Sashank and Danji. Okay, so now we're talking about trying to do some real convergence bound for Adam and with some like more intrinsic notion of quantity about this complexity. So let's first go back to the nature of adaptivity. What does adaptivity mean? It means that there was something you have to choose before you start your optimization run, but now you don't want to choose them manually. You want to have a single algorithm and choose these things adaptively throughout the training process, and hopefully they are as good as you can choose it from the beginning. Okay, so in my opinion, the adaptivity is not just a description of the fact that you are using a time-varying geometry based on path gradient, but it's really about you are trying to achieve some kind of like guarantee, which is kind of as good as if you do some best option, best choice from the inner side. Okay. So basically, what I'm trying to do is that just think about this two-dimensional case. You have a bunch of ellipsoids. Okay, each of them is different, like per scale Euclidean norm, and atoms can be intuitively thinking as you are trying to beat with this family of Euclidean norms, which are all just smaller ellipsoids which contain this infinity number. Okay. So basically, it has like this. It cannot be like this like ellipsoid in this direction in like 45 degree because you have to use the diagonal precondition. Okay. And this is what happens for these norm balls in the dual space. Okay. So basically, these norm balls, if they take the intersection of all these norm balls, they become the infinite norm ball. So it's a kind of like hinting the connection between adaptivity and the infinite norm ball. And I will talk about this meta algorithm. So I forgot to put the, okay, yes. It's by Gupta, Koro, and Dinner. So it's like a template for adaptive algorithms published several years after the initial adaptive algorithm like Adagrad in 2011. So we try to generalize this single algorithm to a general meta algorithm, which if you identify a family of preconditioners H that you want to compete against with, you can run this algorithm. You can instance this template with a different resulting algorithm. And if you choose this family of H to be diagonal matrices, so things like this, you can choose this to be, for example, diagonal matrices, then you get diagonal Adagrad. And if you choose this to be like all those matrices, then you get full matrix Adagrad. And you can also choose this family to be just multipliers by identity. Then you get this Adagrad norm, which is single parameter version. So this template was pretty cool that you can derive all this existing adaptive algorithm from this template. But one issue is that basically you have to still do the proof case by case. You don't have unified proof for all these algorithms because it's not always the case that this template end up with a meaningful, like sensible algorithm that their proof technique would even work. So in this work, we kind of like identify a key property which makes this template always work, which is so-called like this well-structured preconditional family. So basically, the observation here is that to make this meta algorithm work, you have to choose your set of preconditions H to be the intersection of two things. The first thing is of course this set of all the positive definite matrices. The second thing is that it has to be a subalgebra, so it's a K. So K is some matrix subalgebra, meaning that it's closed under addition and multiplication. Okay. So what are natural examples that?
What's subalgebra then? What's subalgebra?
So basically K is a set of matrices.
Yeah.
And it's closed under addition and multiplication.
What do you call this? Subalgebra then?
Subalgebra of the all matrix algebra.
Oh, subinstance space,
Yeah,
subspace. Okay.
yes, yes. Okay. So I'm not going to take the details of this, but I'm going to show you some examples. I just taught this in our convex optimization course. So these are kind of like the examples we are using in practice, and we can prove their algebra, so they're you have nice result for this. Like this is basically you are recurring everything same to one diagonal and use this usual diagram. And this is like blockwise diagram norm. Like in each block you can have the same quantity. And this is full matrix diagram, like something people used to think this is like ideal, but we are never able to implement this due to like compute and memory limitations. And this is blockwise full diagram, and you can maybe we are actually using this in some like papers like KFAC. And this is different. It's called like left-sided shampoo. So it's like one-sided shampoo. Basically, this one is a new thing that we actually can provide a convergence rate for, which is the algebra looks like this. So it's defined for matrix domain. So it's like mapping, linear mappings from matrices to matrices. And because it's matrix, so you can write the linear mapping in a specific form. Like you can multiply this like non-trivial matrix on the left side of the matrix and do nothing on the right side. And the original shampoo does multiplication on both sides, and turns out that has an issue. The issue is that the space that is corresponding to is not subalgebra. It's not closed in addition, and therefore we cannot really prove a nice convergence rate for that. And it's funny in the sense that though shampoo works pretty well in practice, but the original paper proposing shampoo, they prove a convergence rate for shampoo which is worse than diagram norm. So this is still open, and we don't know how to fix this. Is this a fundamental issue or just like some technical issue we can be resolved in future more fine-grained analysis? Yeah. So, but the real punchline here is that throughout this process we identify some like new smoothness notion. I think it's interesting and can be, and I want to present here to be used to comparison for this fixed norm convergence rate. So now I have this notion of like adaptive smoothness. I also have this like an notion of norm based on this family of geometries. So basically, this new convergence rate is saying the following thing. The adaptivity means that you can try to upper bound the final loss of these adaptive algorithms by picking the best geometry in H to reduce the smoothness. But what you have to pay is that you have to pay the largest radius or the R square over all the geometry in this family. So this is notion of adaptivity. You try to be as good, be a best one in terms of the curvature, in terms of smoothness, but you're paying a lot in the radius. And in this case, in the case of diagonal undergrad, this thing basically becomes the infinity norm. Okay? And this thing becomes the trace of the smallest diagonal, the trace of the smallest, the smallest trace of any diagonal matrix who can dominate the Hessian of the loss function. Okay. So with this analysis, we can see the infinity norm actually pops up here. So it's somehow it's related. But on this side, we're actually not getting infinity norm. We're getting something different. It's not a fixed normal smoothness, but instead it's a adaptive smoothness. It's a minimal smoothness over a bunch of norms. And this also challenges a bit conventional thinking in this like adaptivity community. We used to think that the more adaptivity you have, the better the algorithm going to be in terms of like iteration-wise convergence speed. So if we have infinite compute, So we can really want to do full matrix algebra to solve this gigantic matrix and do matrix inverse. But it turns out it's not the case because we still have the other term, which is about the family radius. Using a too large geometry class would make your first term very large. And we test this empirically. We don't have lower bound, but we test this empirically. We actually come up with a very simple practical loss function just to make this like one-sided shampoo beat the full matrix algebra. Okay. So here the message is that like a larger family is not automatically better. Structure is like an inductive bias. You actually want to match your prior, like the family of geometry, the geometry family, to the geometry of the underlying loss. Okay, so now we have two related smoothness assumption to infinity norm. One is just the infinity norm based smoothness, and the other thing is this adaptive smoothness for Adam, right? And I want to compare them, and I want to also understand how we can best utilize them. So this is based on the following result is based on joint work with Shuo Tianhao and Beining. Beining is my one of my PhD students who is currently I think 30 PhD student in Chicago statistics. So we just say this, like I do want to understand the difference between these two rates. So it turns out it's fairly easy to show that this adaptive smoothness is always larger than the smoothness of F over this family norm, which is basically the soup of the H norm over this family. So I take normalized steep descent on VDK on this norm because I want to match the first term. So in case of diagonal geometry, I'm comparing the convergence rate of Adagrad versus SunGD. Okay. And it turns out if you don't have noise, it means SunGD is always faster than Adagrad. So here the actual question is this like adaptive smoothness notion just redundant? Do you want to even talk about that? Why don't just use this notion and just use this algorithm and disregard this? Does this adaptive algorithm really add anything beyond the normalized steep descent? Maybe this SunGD is something we ignored for a very long time and we should just use that. And empirically, SunGD actually works pretty well. There's a paper by Google in 2003 and showed that like they can achieve like similar convergence speed as Adam within just a SunGD. So it's very plausible. So for the interest of time, I'm just going to quickly give the answer. So the answer is no. So adaptive smoothness is not is actually not redundant. It is indeed a stronger assumption, and it can give you a stronger convergence rate in some case. And the point that you have to use momentum, at least in smooth case. So what we show that is in the smooth case, if you have adaptive smoothness assumption, you can actually do acceleration. Meaning this rate for smooth function optimization is from 1 over t to 1 over t squared. And this is consistent with the gap in practice that like Adam is typically much faster than Adagrad, the momentum-free version. So one thing I didn't put here, but is that if you only have the infinity norm smoothness assumption, there's a paper by Guzman and Nemirovsky in 2015 actually showed that you cannot get acceleration for infinity norm smoothness. So basically, Frankov on infinity norm ball is tight. It's like minimax optimal. And this is like saying that fundamentally, infinity norm smoothness is a much stronger assumption than this adaptive smoothness. So because you are taking a much stronger assumption, so you don't really enjoy the benefit of acceleration, and empirically, you really cannot make SunGD converge faster by applying momentum on top of SunGD. It doesn't work. The empirical doesn't work. So, yeah. So there are still a lot of open questions here. For example, does this like extra T really exist in like practical training where the loss is like non-convex, maybe only locally convex, and does this actually compensate the gap between adaptive smoothness and this infinite norm smoothness? Also, this notion of adaptive smoothness is global. Can we have like local notion with adaptive smoothness? So, question?
Yeah. So you mentioned that there's like different inductive biases for these algorithms that result in different training speeds. I wonder, like this is like a very like abstract idea, that I wonder if it's not a specific inductive bias of like L infinity or nuclear for like mu1 or any other thing for other algorithms, but it is that for neural networks, because the way the neural networks are formalized is like there's a lot of equivariances in the function space that we have, and we have an update direction according to the gradient. The algorithm that restricts the geometry to the smallest volume of possible updates at every step while still being in the steep direction is the algorithm that breaks the equivariance and symmetry the most, and that's why it gets better results. And that would explain why Newton gets better results at mu1, gets better results at atom, gets better results at GD, that GD like has no restriction there.
Okay, that's a very good question, but let me just rephrase. I think this is also the point I want to make next. So, I would rephrase it as like where does this like geometry-related assumption come from? So if you have different architecture, you can have a different loss space and this like objective function. Like by doing reparameterization, you're going to change your smoothness structure, the landscape loss on this space. I think is more talking about what happens in this function space, and then you can directly see that your parameter prevents your next iterate in terms of function to go to some area, right?
Yeah.
But I think that's like another way to think about the question I'm going to talk about next. But I'm really thinking about in parameter space. So in parameter space, there's no any restriction, just do unconstrained optimization. So I'm not even talking about learning here. I'm just talking about optimization.
Even in optimization, like you want to go from one saddle to another saddle, and there's like a lot of saddles around you. Each of these geometries enforce that, okay, these are the only saddles that you can go to. So you, like the space of reduction, like this is abstract, but I feel like it could reduce the...
Okay, so maybe let's keep this discussion offline. So let me finish this. I have like one last piece. So okay, this is something I'm actually thinking is I'm working on this, thinking more about this in the in current days, which is this like part 2. So the part 1 is more about like algorithm side. It's like a very abstract, kind of like solve the problem of like what kind of smooth assumption to utilize this kind of smooth assumption. How should I design my algorithm? And given this algorithm, it works empirically. How can I identify smoothness assumptions or like maybe noise assumptions that make this algorithm better than some other candidates to better describe what happens in practice? The second part is more grounded to the architecture itself, the practical training. So actually, I want to understand in an end-to-end way, how does this nice property actually emerge from this architecture and data distribution? And therefore, like this is important if we want to use this kind of thinking to design future algorithms, or like to just make the choice of optimizer based on which layer you should use, what kind of like norm. So we don't have much results here, but maybe many results here. But I'm just going to show you like the idea with this single result, which is the benefit of the infinite geometry over this heavy-tailed distribution. So it goes back to an empirical paper written by intern Robin Yadav. So basically, he with collaborators empirically showed that if you have a heavy-tailed class imbalance, if you think like the lexicon prediction, you have like lots of classes, and some are like more fun than the others. Maybe they follow a parallel. In this case, they observe that Adam and Sun GD optimize much better than GD and normalized GD. And this is not only for lexicon prediction, and they also try to mimic this behavior on like image classification by introducing like artificial class which are heavy tail and other settings. Like linear prediction. So basically the curve looks like this. This is red one is adult, and this blue one is SunGD, and the two other GD variants, they coincide and they're very slow. Around last winter this time, maybe it's earlier than May. So Robin reached out to me and asked me for like he's interested in building TTIC and worked with me, and we got interested in this project, and so we together worked on like turning this empirical phenomenon into a more kind of like theoretical understanding in the summer. And our approach is basically try to simplify this phenomenon. So we start with transformer, and we try to find the minimal architecture to make this phenomenon work, and still hopefully we can do some analysis. So we kind of like remove the tension MLP layers, it still holds, and we make it only one layer. We first make it one layer, and then remove the tension MLP layers.
In what sense is it transformer and not just a linear classifier?
So point to simplify it and see what is the P part that makes it work. Okay. So first one layer, and then remove MLP and attention. Okay, so it's only like embedding layer times the classification layer, and then we only train classification layer. So it's like really like a random linear feature, and then we fix the embedding dimension to be 1. Okay, so what is that? So in the end, we're just training this. So we have some token distribution P, and we're training a softmax, and the X is of dimension, same dimension vocabulary. Okay, and just on this loss function, you can observe the same benefit of Adam and SunGD over GD, just a softmax. Okay, and we can prove theory for this because this convex optimization is very easy. And this is a phenomenon we can kind of like reproduce over some like realistic data, which is entry bank, and this is like synthetic power law. Basically, you see like curves like this. You can have SunGD and Adam much faster than normal SGD.
If you use Adagrad, does it work like Adam in this case? Or?
I think it's similar, but we didn't really try Adagrad very hard. But I think it's usually slower than Adam. So some very brief theory, very simple theory.
Yeah. Zero time.
Zero time. Sorry. Okay. So the punchline that you can prove that for SunGD is like really 1 over T rate, log D over T rate. But for GD, this is you have to wait for D steps. Your D is the size of vocabulary, or you will diverge if it's too large. Okay. So you can skip this. Skip this. Just jump to conclusion. So basically, I'm trying to convince you this geometry is very useful lens for understand modern optimizer behavior, and adaptive method is to go beyond active geometry to be understood and explore family of geometries instead of like single norm. And I think we should study more on the architecture and data's impact on the favorable geometry for the optimization. That's it.
Additional questions for Zhiyuan? So there's something I'm confused about with this, because most of the parameters are somewhere like in the middle. Why do you get this strong axis alignment bias then for parameters like in middle layers? So you're saying that the geometry is something inherently axis aligned?
No, I'm not saying it's inherent, but it's just like the amount of axis aligned is better than just random L2 geometry. So if you think about this, like you have like matrix structure, right?
Mm-hmm.
That's not random, and you also have like layer-wise structure, right? Like it's not random. And if you break this, I mean, we can probably say more details about like our like various like ablations on how it will rotate. Yeah. Like you can think about rotation within a layer and a cross layer, and this cross layer rotation is hurt a lot.
I see. So does it make sense? So
it makes sense to use.
What the Muon tries to do to capture this the fact that it doesn't do it directly, but I mean I guess maybe can you capture more directly then is the correct preconditioner then to use or correct H to use the one that exactly reflects it? The
So
fact that there's
there are some work.
some coordinates can rotate and some can't.
Yeah, so there are people trying to do that because there are people trying to do this, okay, splitting the blocks, and each one is a skill. So this saves memory and can make you afford to train large models.
Or even look there.
Yeah. So this is shampoo, something Google is trying to promoting. But yeah, I think so. So that's why like this kind of like field very active, but there's no consensus basically, so we don't know.
So for muon, it doesn't have axis alignment. Is that right?
So that's like kind of like muon takes the max norm of the operator norm of each matrix parameter. So it's doing matrix by matrix, and for each matrix it's rotating. So you say
Yeah, but it's invariant to rotating each matrix, right?
Yeah.
So then
No,
works well.
It's not completely invariant to rotating. It's only invariant to like rotation on both sides, right? If you think about like random rotation on d square to d square mapping, it's not. Muon is only invariant to like
rotation on
To
right
rotation
and
of the
left,
metrics
right?
as opposed to rotation of the vectorized. If I get gradient sin is invariant to
Yeah, but
vectorize the
I'm
metrics.
just saying like if muon works well, doesn't it suggest the coordinate is not important? Like
yeah. So it's not the same like called the annual story. So it's a simple for improvement.
Any additional questions? Okay, great. So let's thank Zhiyuan again. And